So here in this section, we'll get an introduction to graphing and functions. Let's get started with the definition of an ordered pair. So an ordered pair generally will look like parentheses and will have a number in the x-coordinate location, followed by a comma, followed by a number in the y-coordinate location. So one thing to keep in mind is these both are numbers. Right now I'm just writing letters as a placeholder. They're both numbers and they're written in a specific order. So as we learn about this topic, we need to see the first number as the x-coordinate, then the comma goes, and then the second is the y-coordinate. And soon I'll describe more specifically what the x and y coordinate is, but at this point just keep in mind that whenever you see this parenthesis, number, comma, number, close parenthesis, that is an ordered pair, and the number in the ordering is indicating a particular meaning. So as we're learning about this topic, let's look at a specific example that will help us see what this ordered pair means and how we can deal with it. So to graph an ordered pair, we deal with what's called a coordinate axis. So here I've drawn a picture. And if you're trying to do this on your own paper, say you don't have this in front of you, you can always draw a coordinate axis by drawing one vertical line, cross it in the middle by a horizontal line, and then you can draw little tick marks out and try to draw these somewhat evenly spaced as best you can. So for instance, I'm drawing the tick marks out to show moving so many units in the x direction. So let's count it. This is the first unit in the x direction, the second unit in the x direction, the third unit in the x direction, the fourth, and so on. And when you move to the right in the x direction to the right is positive values. And when you move to the left in the x direction, that's negative values. Because one thing that we think about is this exact point in the middle is where x is 0. It has no x distance. If you move forward, you're going in the positive x direction. But if instead you started at this x equals 0 and you move backward, you're going in the negative direction. And that's why you can see that here this first tick mark is 1, this one is 2, this one is 3, this one is 4. But as we move in the backwards direction, do you see now we have negative 1, negative 2, negative 3, negative 4. So the horizontal is the x-axis, which we see marked here. Now the vertical is the y-axis. So as you move up in the y-axis, it's positive. And as you move down the y-axis, the values are negative. So here we can see that marked here. We've got our y-axis marked. And we've got, as we go up, the values are positive 1, 2, 3, 4. And as we go down, it's negative 1, negative 2, negative 3, negative 4. And to help you remember which one's x, which one's y, and reading the x and y ordered pair coordinates, when I think of the ordered pair coordinates, if you go through your alphabet, you'll see that x does come before y. So if you're ever unsure which one is which, just think in terms of the alphabet, x comes first, then it's followed by y. And in terms of graphing it, when I draw my x and when I draw my y situated like this, kind of a small memory device I used is I think of the y drawn in this way has a very clear vertical bar as part of it, so it's the vertical axis. Whereas the x, it's kind of got 2 feet on the ground, it's the horizontal axis. So both those are just memory tricks to help you keep the two things straight. Let's start actually graphing these ordered pairs now that we've introduced the topic of the coordinate axis. So in this example, we're asked to plot the point 2, 3, and then separately we'll plot the point -1, -4. Now here's where I would encourage you to pause this video and try this on your own. This will help give feedback if you're following along with this topic. Unpause and I'll give a guided solution. So take a moment, please pause the video and try this on your own. Okay, so hopefully everybody's had a chance to try this on their own. Let's plot the point 2, 3 in blue. So I always, as I'm practicing, I might write this reminder x, y. So I know the x is the 2, the y is the 3. And always plot, I usually do x then y. And if you have a pattern, you're going to be more consistent. So plot the first number first. So it says go over 2 units positive in the x direction. So find 0 of x. Go over 2 units. So this is x in the 2 units that are positive. And then how many units do we go in the y direction? It's a positive 3. So I go from that point up 3. 1, 2, 3. This point is where I'm going to plot. And just to visualize that, we move 2 units in the x direction and then up 3 units in the y direction. So these aspects of the drawing is helping me find the point, and then the only part of my final answer will be actually plotting the specific point 2, 3. Okay, now let's plot the next point in red, -1, -4. So I'm going to go in the x direction first. So I'm going to find, personally, my center point. Okay, and I'm going to go -1 in the x direction. And then in the y direction, it says go -4. So I'm going to go down 4 from there. So down 1, down 2, down 3, down 4. And I would plot my point right here at -1, -4. So we've gone through an example of plotting x and y coordinates. You'll have examples of that in the practice textbook homework I assigned. So remember, plot the x coordinate first and then the y coordinate. The x is positive as you move to the right, negative as you move to the left. The y is positive as you move up and negative as you move down. Now, a different thing that we talk about in terms of the coordinate system, whenever we just draw our coordinate system, remember the vertical and the horizontal line, can you kind of see that it splits the overall graph into 4 places? And I'm trying to sketch these here to show our 4 quadrants. As we draw the coordinate axis, it splits it into 4. And specifically, we label these 4 quadrants by name so that we can quickly reference it. So the name for this quadrant is quadrant 1, written in the Roman numeral. And the thing to keep in mind here is in quadrant 1, both the x is positive coordinates and the y is positive coordinates in quadrant 1. And that's what it says here. Now in quadrant 2, and as we're labeling it, we go counterclockwise, so we go from 1 all the way around. So quadrant 2 in Roman numerals has x coordinates negative and y coordinates are still positive, as stated here. Now quadrant 3, which we label in Roman numerals, give yourself a minute and think, how would you describe its x and y coordinates? Are they positive or negative? So quadrant 3, we see both the x and the y are negative because it's to the left in the x direction and down in the y direction. So it's when the x is negative and the y is negative. Okay, let's finish up quadrant 4, the last quadrant split up in our x and y coordinate, written as the Roman numeral 4. What is its x and y coordinate in terms of positive and negative values? Okay, so we can see here the x coordinates are positive, but since it's below the x-axis, the y coordinates are negative. So as we're wrapping up this section, remember we've just kind of layered a definition that when you draw the x and y coordinates, we can give names for the different sections. This is section 1, where both the x coordinate is positive and the y coordinate is negative. So every coordinate point in this section would have positive x values and positive y values. Now quadrant 2 has negative x values and positive y values, so everything that lives in this section has negative x values but positive y values. Quadrant 3 has both negative x and negative y, so everything that would be in this section has negative x values, negative y. And finally, quadrant 4 has positive x values but negative y values. So just for a quick practice, can you see here I've drawn a coordinate plane with a point marked here? What quadrant is this point located in? Quadrant 1, 2, 3, or 4? It is in quadrant 2. Okay, good work. Let's do another practice. Do you see the new point I've drawn? What quadrant is it in? It was in quadrant 1. Okay, let's do one more. What about this last point? What quadrant is it in? 1, 2, 3, or 4? And that one's in quadrant 4. So in this section, we're going to combine what we just learned about points and our x and y coordinate, and we're going to add in a new idea of an equation. So let's first introduce this equation. I think it will help starting with the example. I'd like to highlight here, we've got a letter y, and we have here a letter x. Now the way you're going to see these letters x and y is they are placeholders. This is a placeholder for x coordinates. We write them as variables because we want to be able to put in many different x values to this rule and get out the corresponding y value. We don't just want a single x value because we're plotting an equation, not just a single point. And then this y is a placeholder for y values. And the way this equation works is this is a rule that says the x and the y values are related in a particular way. The way that they're related is any x value you start with, we're going to multiply it by 2 and then take that value and add 1 to it. Whatever you end up with after doing all of that is the y value. So equations are just stating particular relationships between the x value and the y value, and the relationship they're stating is explained by the mathematical equation. So in this case, it's 2x plus 1. And we can graph this equation and see what it looks like on our coordinate axis by picking values of x and plugging these x values into the equation and seeing what y value we'll get. Now, because these are our notes, we nicely have a graph set up and a table set up. But let's say you're doing a problem for practice from the textbook and the table's not set up on your notebook paper, nor is the coordinate plane. How would you get started? You would get started by, I draw my table values. I'd say x and y and draw a nice long table. And then we pick nice values of x. Since we can choose, let's put in things like 1, 2, 3, 0, -1, -2. I'm not going to put in 1.25 as an x value because even though that would work in the equation, it's not going to give me a nice, usually integer answer as a result. So I like to pick a little bit of the negative values of x and a little bit of the positive values, usually picking 0. So let's start with like -3, -2, -1, 0, 1, 2, and 3. Now, just to clarify, the reason I'm explaining it this way and not using our generated table is to give you an example of what you would do if you were doing your own homework. And then we'll follow the notes table as well because it will have the same values. Notice it covers -2, it covers 0, and it covers 2. So here we're just plotting more points. And then the way this works is I take my -3x value and I plug it in for x in this equation. So I would get 2 times -3 plus 1. Now 2 times -3, if I use my calculator, I'll see is -6. And if I add 1 to it, I get -5. So when x is -3, the corresponding y value is -5 by following the rule 2x plus 1. Let's together do the next calculation for x is -2. So I'd take x value of -2 and I plug it into this equation. Often, as you're getting used to it, I encourage you to write out the equation with the new value plugged in, 2 times -2 plus 1, calculate from there. 2 times -2 in your calculator is -4, plus 1 is then -3. Okay. Now, take a moment and try to think, what would you do next to calculate the y value when x is -1? I'd ask that you pause right now and calculate the next few values on your own. This gives you a chance to test your understanding. Unpause and you'll see my detailed solution. So when x is negative 1, I plug it into the equation 2 times negative 1 plus 1. 2 times negative 1 is negative 2, plus 1 is negative 1. Continuing at 0, 2 times 0 plus 1. Now anything times 0 is 0, so that becomes 0 plus 1, which is just 1. 2 times 1 plus 1 is going to be 2 plus 1, which is 3. 2 times 2 plus 1 is 4 plus 1, which is 5. 2 times 3 plus 1 is 6 plus 1, which is 7. So here I've plotted a good variety of points. I've plotted some negative x values, I've plotted 0, I've plotted some positive y values, and using the equation I found the corresponding y values. So this table does a very efficient way of writing the points as an ordered pair, negative 3 comma negative 5. And that's what we want to see this table as. This table is just an efficient way to write out all, oh no, 1 second there, I messed up. So this table, as I was saying, is just an efficient way to write out coordinate pairs. Excuse me, ordered pairs. So for instance, this negative 2, negative 3 represents the ordered pair negative 2, negative 3. Negative 1 represents the ordered pair negative 1, negative 1. And you see the pattern. The x values of the table are the x coordinates. The y's are the y coordinates. So I can actually see what this looks like by plotting points. So step 1, find the points in the table. And here, if I wanted to fill out the smaller table I did, I see I've already got those values. And then 2, I'm going to graph the points on a coordinate planes. So I've got my coordinate plane drawn here. Again, if you didn't have this on your paper, you'd draw a vertical line, a horizontal line, and then you'd start making even tick marks across the x-axis, even tick marks across the y-axis, and drawing from there. So here I've got my graph. So I'm going to graph in the x direction, negative 3 over. So that's 1, 2, 3. And on this graph, if you'll notice, my y values are at a different scale than my x ones here, just because I was running out of space. It goes up by 2, so here's my 1, then 2, then 3, then 4, then 5. So just, if you've already got a pre-drawn graph, make sure the coordinates are the same in each direction. If not, accommodate for that. So for the first point, negative 3, negative 5, I'm going to go negative 3 in the x direction, and then I'm going to go negative 5 in the y direction. And I see that my graph actually does not go far enough, so I'm going to have to go down and kind of add a point. So I go 1, 2, 3, 4, 5 in that direction. So bring that over, and I'd get this point. So we've graphed this first point. Let's graph the next point, negative 2, negative 3. So I found my value negative 2 here, and I go down until I get to negative 3, which is about halfway here. So I've graphed my second point. Now let's graph negative 1, negative 1. So I go over to the negative 1, and then down negative 1. Line those up. Okay, now 0. Where is 0? 0 for the x and y value is here. So I go 0, so I have 0 distance in the x direction, but I go up 1 in the y direction. So I have a point right on that axis. And then, if y'all will, let's pause, and I'd ask that you'd graph the next ones on your own. Unpause to check your work. I really encourage you to always take these opportunities to pause and unpause. It gives you a chance to, in the moment, assess whether you're getting the problem right or wrong. And then you can learn from that if it happens to be wrong. So please do pause right now. So hopefully everybody's had a time to attempt that. Let's continue. So for the x coordinate 1, 3, x goes over 1, 1, and then up 3, and I get that point. And I'm just kind of check marking to keep up with my list. And then 2, 5, so I go over x in the 2, and then up 5, mark that point. Last point for me, 3, 7, so I go over x is 3, and then I see my actual y-axis stops at 6, so I'll need to extend it, and I go up 7. Looks like I'm going to have to move something. And I go up 3, over 3, and up 7. And it happens to be when I plot on my points, I see they make up a very nice straight line, because 2x plus 1, as we'll learn later in more detail in upcoming sections, is the equation for a straight line. So then we've graphed the points. Step 3 is connect the points. And in this case, when I connected all the points, they connected in a straight line. So whenever you get an equation and you're asked, graph the equation, what are the steps? Involved in those steps is to, step 1, write a table and pick some x values that are negative, the x value 0, and some positive x values. Write those down in your table first. We wrote down the x coordinates first, right? Based on those x values, you plug each of them individually into whatever equation you have and follow the rule set forth by the equation. Then record the y values as you make each of those calculations like we did here. When you're done writing your table, then you graph the points using what we know about x and y coordinates. I graphed all the points at first. Only once you've graphed all the points do you connect the points by starting from the left and then following whatever pattern you see. Now let's practice that with our next example. But remember, when they say graph the equation, it's implied 3 steps. Make a table, fill out the table, plot the points, connect the points. Here, let's continue with our next example. So here we're given the equation y equals negative x squared plus 4, and we're asked to graph it by choosing several values for x and then finding the corresponding y values. And then after that, we'd plot the points and then connect them from left to right. Now for this example, some points have already been chosen for us, but if the points aren't provided as the x values, remember to pick a few integers that are negative, 0, and positive. So let's plug negative 2 into negative x squared plus 4, and anytime there's a square or any exponent, I really encourage you to be careful as you're typing this into the calculator, because we do have to put it in correctly. Negative 2 squared plus 4 is how we should type this in, because the negative is just a value out front. Only the x value is being squared. So you have to square the entire x value. If you instead, in many calculators, just type in negative 2 squared, that will give you the answer of negative 4, whereas negative 2 in parentheses squared is 4. So as a caution, anytime you have an exponent, make sure you put your input inside parentheses to make sure it calculates correctly. So I'm going to do the exponents first. When you're thinking about which operation to do first, we have a common phrase. It's an acronym. Please excuse my dear Aunt Sally. And it stands for parentheses, exponent, multiply, divide, add, subtract. It tells you go down the list whenever you're working through simplifying an expression. So we're going to deal with our parentheses first and then our exponent. So we type in negative 2 squared in parentheses, and that will give us 4. And then the negative that was waiting outside gets applied. So now we can do the next part of our list, which is add. Negative 4 plus 4 is 0, so we get 0 for that value. Now why don't you pause and in a similar fashion try to find the y values at x equals 0 and x equals 2. Unpause to check your work. So next, as I substitute x equals 0 into the expression, I have negative parentheses 0 squared plus 4. I'm going to deal with the exponents first. 0 squared is 0. I bring down the negative, and then I add 4. Now 0 is always 0, whether you have a plus or a minus in front of this, so this becomes 0 plus 4, or I could type it in my calculator and I get the answer 4. So next up, when x is equal to 2, we get the expression negative 2 squared plus 4. Deal with the exponent first. 2 squared is 4. Bring down the negative that was in front. Plus 4. Negative 4 plus 4 is 0 again. Now I'm going to plot these points, so I go over the x direction of negative 2, and 0, remember, is always on the x-axis. It has 0 y height. Think of above the x-axis as positive y height, below is negative y height, so at 0 is right on the axis. And then at 0 of the x-axis, so I have no x distance, I'm at the y-axis, I go up 4, and then I go over to 0 here. Now, this graph happens to be what's called a parabola. You don't have to know the name, but a square, anything that is of the form x squared in it, will be a parabola, and it's going to look either opening up or opening down. So from these plotted points, I can tell that if I connect it, I need to connect it opening down. And that might just be something to remember. For anything x squared, you have that basic shape. It's either an upside down U or regular facing U. So let's just recap what we did in this graphing problem. Step 1 is we plotted the points. Okay. Step 2, or I should say calculated the points. Step 2 was we plotted the points we calculated on the graph. Step 3 is we connect the points from left to right. So remember those 3 steps when you're asked to graph an equation when plotting points. So up to this point, we've worked with some equations and graphing equations, substituting values into the equations, and now we're going to get a particular category of equations called a function. So not all equations are functions. Functions have an added constraint that must be met, and the extra step that must be met in order for an equation to be called a function is that each input, think x, has exactly one output, think y. So a different way to phrase that is for every x, there's only one y option. And in general, the set of all the possible input or x values is called the domain, and all the possible outputs or y values is the range. So remember those 3 definitions. A function is an equation with the particular behavior that every input has one output. So every x goes to exactly one y, and the domain is all the x values for the function, and the range is all the y values for the function. Now function notation is, up to this point, I think we've seen a lot of y equals x squared, for instance, minus 3x plus 2, so it's x's and y's. All function notation does is instead of saying y, it writes it as f of x. And what it's writing here is the function of x. So think of f of x as a replacement for y. And the reason we do that is the notation clearly tells us this is a function and the input variable is x. So with this notation, this is the exact same thing as the equation y equals x squared minus 3x plus 2. The only change is we're writing it as the function of x to make it clear that this is a function and the input variable is x. And the way we evaluate this is when it says find f of 1, it's saying for the function f of x as it's described here, find the output when the input is x equals 1. Now how do I know x equals 1? Because that's what's inside the parentheses. I always remind myself the input is inside the parentheses. So that's just something to help you decipher it. Remember the inputs inside the parentheses in function notation. And then at this point, once we've identified the input as x equals 1, we just substitute it into the equation like we know how to do. So This particular equation says every input should be squared, and then we should subtract 3 times the input plus 2. So I have 1 squared minus 3 times the input plus 2. 1 squared is 1, minus 3 plus 2. And then when we combine these together, 1 minus 3 plus 2 is 0. So we could write our final answer as the function evaluated at the input 1 gives us the output 0. So now let's give you a chance to practice. Please pause the video and attempt this example and this example. And then after you've worked it out, unpause and check your work with the detailed solution that's coming next. So here we have our function. Now in this case, our variable is just named differently. Just like f of x, now it's a different letter, g of x. So it's just saying g is your output, x is your input, and it's determined by this equation. We're asked to find the value of the function when our input x equals -3 because it's inside the parentheses. And then the equation that determines it is here. So I do 2 times the input, which is -3, plus 5. 2 times -3 is -6 plus 5. That will simplify to -1. So the function evaluated at -3 is -1. Moving on to the next example. Again, this is a different letter, but don't let that throw you off. You still follow the function notation pattern, which is h is your output, x is your input. It's determined by this equation. Here we're looking for when the input is 2. So I say h of 2 is equal to 1 over, the x value is here, so 2 minus 1, follow the pattern. I'm going to simplify 2 minus 1 is 1. 1 divided by 1 is 1. So h of 2 equals 1. Now, just a few minutes ago, we introduced the definition of function, and we mentioned that it is when every input has exactly one output. And there happens to be a very nice tool for helping us identify when graphs are functions. So if you're ever given a graph, that visual depiction of an equation, then you can quickly determine if it's a function if it passes what's called the vertical line test. So the vertical line test is when, here it's defined, a graph is a function if and only if no vertical line that you could imagine drawing will intersect the graph at more than one point. So here in this example, do you see my graph is this circle? And this dotted line is what I'm asking you to think of, an imaginary vertical line you're drawing. So at any point of the graph, if you draw an imaginary vertical line, would it hit the graph of your equation in more than one point? And for instance, in the vertical line I've provided here over the equation of the graph, do you see it hits it at point A and B? In fact, any vertical line I imagine drawing would hit the graph here, with the exception of this vertical line that hits it only at one point. But again, it's not that if there's a line that will pass it through 2 points, it's not a function. So even if there's a single line where if you draw it, it hits the graph in 2 places, that means it's not a function. So here I would say not a function because the imaginary vertical line hits the graph in 2 places. So the vertical line test is a great tool. It can only be used when you're given a visual depiction of the graph, but if you're given a picture of the graph, just imagine drawing vertical lines to the graph, and if you see it hit in more than one place, then it's not a function. If there's no vertical line you could imagine that hits it in more than one place, then it is a function. So let's go through some examples of this. So in this example, we have 4 different graphs, so I'm going to draw this line to make it clear. Example 1, 2, 3, 4. Let's go over 1 together very carefully, and then I'll ask that you do 2, 3, and 4 on your own when I pause, and then when you unpause, you'll see the solution. So zooming into 1, we need to tell the instruction said use the vertical line test to see if they are functions. So our answer is either going to be it's a function or it's not a function. So here's your graph, and imagine drawing vertical lines, and particularly if this is on a screen, use your finger to trace with me. Imagine these vertical lines. Do you see it hitting the graph in more than one place for each line? Any vertical line that I'm imagining drawing, would you agree it hits in only one place? I don't have any of these multiple hits per a single vertical line. Because I can't find a single place where a vertical line would hit the graph in more than one point, this is a function. Now, if you would, take a moment and pause this video at this moment, attempt problems 2, 3, and 4 on your own, and then unpause to check your work against my solutions. So let's continue our examples in order. Now I'm at example 2. I see the graph is depicted here. I'm asked is it a function or not using the vertical line test. So I'm going to imagine drawing vertical lines, and I'm going to look for if it hits the graph in more than one place for each line. So far, I think you'd agree that there is only one hit per vertical line. So this is a function. I'm not seeing those repeated hits through the graph. Vertical line test tells me this is a function. Now let's look at example 3. I'm going to draw an imaginary vertical line, and immediately, whichever vertical line I draw of these, would you agree that it hits more than one place? For instance, if I draw this pretend vertical line, I've got a hit here and a hit here. So that tells me this is not a function. And while we're looking at this, let me just quickly explain why the vertical line test works. Remember the definition of function. The definition of function is that each input, or x value, has only one output, or y value. The vertical line test fixes x values. For instance, this vertical line goes through this x value. But do you see for this x value, this graph has the y value here. If I look at this x value, you've got a y value here and a y value here. So in this graph, a particular x value has more than one y value. That's why this is not a function. So the vertical line test is a visualization of the definition that each input can have only one output. If any single input has more than one output, then the graph is not a function. Let's move on to our last example. So here in example 4, I need to apply the vertical line test. So with my pen, or if you don't have this, imagine with your finger drawing vertical lines, and you're looking, do we ever hit more than one point through any vertical line I could imagine drawing through this graph? And here, no matter what vertical line I imagine, it's only hitting one output. So this is a function. So in conclusion, our only not a function was for this example, example 3. And that's how we can use the vertical line test to quickly determine if a graph is a function or not. So that'll be the end of this video. As always, please reach out to me through our class communication. If you have any questions, I'm very happy to help, and I look forward to working with you in the next video.